All right, today we're pulling back the curtain on the literal foundation of our modern world. We're going to get into the science that's hidden inside every single piece of tech you own, and it all comes down to one amazing element. So let's get into it and uncover the secret of silicon.
I mean, it sounds kind of like magic, right? The idea that the same stuff you find on the beach is somehow the engine behind your smartphone, your laptop, even massive supercomputers. It's a huge, wild question, but the answer starts at a scale that is unbelievably small.
That's it. That's the secret. The entire digital revolution, everything we take for granted, is built on our ability to boss around these tiny, tiny particles, to tell electrons exactly where to go and what to do. So how on earth did we figure that out?
Well, here's the game plan. We're going to tackle this in 5 parts. First, we'll look at how different materials handle electricity. Then, we'll zoom right in on the electron itself. After that, we'll meet the superstar material that literally changed everything, uncover the secret trick that makes it work, and finally, we'll see how it all comes together inside the gadgets in your pocket.
Okay, first up, let's meet the 3 main characters in this whole story. You see, not all materials are created equal when it comes to electricity. They each have a very distinct personality, a different way of letting a current flow, or not. When you really boil it all down, the whole story comes down to one thing: free electrons. Conductors, like copper, are packed with them, which lets electricity flow super easily. Insulators, like rubber, have basically none, stopping electricity cold. And then there are the semiconductors, like our friend silicon. They're in the middle, and they have this incredible property. Their electrons are controllable, and that changes everything.
Okay, so we keep talking about these free electrons. It's obviously a huge deal, but what does that actually mean? What's the difference between an electron that's free and one that's bound?
Let's think of it like this. A bound electron is stuck at home. It's held on a tight leash by its atom, and it can't really go anywhere. But a free electron, it's left the house. It's free to roam around the entire neighborhood of atoms. It's these wandering free electrons that actually carry a charge and create an electrical current.
So a conductor, like the copper inside your charging cable, is basically a massive, wide-open superhighway. It's just jam-packed with free electrons, all ready and waiting for a little push from a voltage to tell them which way to go. The flow is fast, easy, no problem at all.
Now, an insulator is the polar opposite. The rubber coating on that same cable, its electrons are on total lockdown. They are all bound super tightly to their atoms. This stuff acts like a solid brick wall, and it's what prevents that electrical current from going somewhere it shouldn't, like, into your hand. Okay, so we've got a superhighway for go and a brick wall for stop. But to build modern electronics, we needed something way more clever. We needed something that could be either one, on command.
And that, right there, is the absolute genius of semiconductors. They aren't always on, like a conductor, or always off, like an insulator. They're more like a drawbridge for electricity. We have the power to tell them when to open up and let the current flow, and when to close down and block it.
So, who's the star of this show? It's silicon. What's amazing is how incredibly common it is. I mean, it's literally the stuff you find in sand, in rocks. It's everywhere. And that abundance is a huge reason why our technology has been able to scale up so massively. But here's the twist. In its pure, natural state, silicon is, well, it's kind of boring. Electrically speaking, all of its electrons are locked up tight in this perfect crystal formation, which actually makes it a pretty terrible conductor. To unlock its true potential, we have to deliberately mess up that perfection. So if pure silicon is basically useless, how do we turn it from a boring insulator into that controllable drawbridge we need? Well, this is where the real genius comes in, with a process that has a funny name but is absolutely critical. The secret sauce is a process called doping. And you can really think of it like being an atomic chef. You start with a batch of ultra-pure silicon, and then you intentionally sprinkle in a tiny, precisely measured amount of another element, an impurity, to completely rewrite its electrical recipe. This recipe comes in 2 main flavors. For what we call N-type, you add something like phosphorus. It has 1 more outer electron than silicon's crystal structure needs, so that leaves 1 extra electron just hanging out, free to move around. For P-type, you do the opposite. You add boron, which has 1 less outer electron, and that creates an empty spot, a hole, where an electron is missing. So what we end up with are 2 brand new types of silicon.
N-type has extra negative electrons ready to go, and P-type has these positive holes. Now, a hole doesn't really move, but it acts like a positive charge moving through the material, as nearby electrons keep jumping in to fill the empty spot. The point is, we can now create and control the flow of charge on command.
Okay, we've got our special ingredients. We've created our N-type and our P-type silicon. Now for the grand finale. How do we use these to build, the entire modern world? By cleverly combining these two new materials, we can create the fundamental Lego bricks of all modern electronics. We're talking about diodes, transistors, and the integrated circuits that are built from them. First step, the diode. You just sandwich a piece of P-type and N-type silicon together, and boom, you get a one-way street for electricity. It's a simple little component that lets current flow in one direction, but blocks it from going the other way. Super useful. But the real game changer, the invention that defines the modern era, is the transistor. This thing is basically a microscopic, lightning-fast switch with absolutely no moving parts. By applying just a tiny electrical signal, you can turn a much bigger current on or off. And that on-off function, that's the basis for all binary code, the ones and zeros that run our digital lives. And this is where things get truly mind-boggling. An integrated circuit, a microchip, isn't just one transistor. We're talking about millions, and today, literally billions of these tiny switches, all perfectly etched onto a single sliver of silicon. This is the brain of your computer. This is the memory in your phone. It's an unbelievable amount of complexity in a tiny, tiny package. So let's bring it all home and look inside the phone that's probably in your hand or pocket right now. It is a perfect symphony of all three materials working together. You've got conductors, like the copper wiring, moving power around. You've got insulators, like the glass screen, protecting everything. And then you have the semiconductors, the stars of the show, running the display, the touch sensors, and of course, all those incredible memory chips. So there you have it. We've gone from a simple grain of sand to the sprawling, complex universe inside a single microchip, all because we learned how to control one humble little electron. It just makes you wonder, as our mastery over materials keeps getting better and better, what new worlds, what new technologies are just waiting for us to unlock next?